Hello, so welcome back. In the last class, we discussed about uh, the convex programming problem, and in particular, we consider the problem of this type where we want to minimize f of x subject to some inequality constraints and equality constraints. Now, the assumptions that we made was that f and h's are smooth convex functions, and ei's, the equality constraint related functions, are affine functions of the type ai transpose x minus bi. Then under these conditions, this problem becomes a convex programming problem. Remember that for a convex programming problem, we minimize a convex function subject to a constraint set which is a convex set. So, this set x is a convex set because it is a intersection of many convex sets, and we have earlier shown that such a set is a convex set, and we assume that Slater's constraint qualification holds for x. So, that means that there exists at least one point which is in the interior of the set, or in other words, the set x has a non-empty interior. And one way to say that the Slater's constraint qualification holds is that there exists some y in the set x such that hjy is less than 0. And as I mentioned last time, that when we say y belongs to x, so that means that clearly ei is equal to 0 for all I going from 1 to m. So, that condition is always satisfied. So, it is just to make sure that hjy is less than 0 for all z, then that means that there exists a point which is in the interior of the set, and we can say that Slater's constraint qualification holds. So, if Slater's constraint qualification holds, then the first order KKT conditions are necessary and sufficient for a global minimum of a convex programming problem. And we saw the proof of this, which was a straightforward extension of the earlier proof where we consider the convex programming problem minimize fx subject to hx less than or equal to 0. Now, what is the meaning of the Lagrange multipliers associated with a nonlinear programming problem? So, let us try to see that interpretation. For the time being, let us consider this problem where we want to minimize f of x subject to the constraint hx less than or equal to 0, and the ideas that we are going to study can be easily extended to a general nonlinear programming problem where we also have equality constraints. So, let us denote the constraint set as usual by the symbol capital X, and let us assume that x star belong to x is a regular point and is also a local minimum. So, let us consider the active set at x star to be the set of all z such that hx star equal to 0. Now, when we want to study the interpretation of Lagrange multipliers, so what we want to know is that if we perturb any of these constraints a bit, then what is the effect of that perturbation on the objective function, optimal objective function, or in other words, suppose we have a constraint set. So, our constraint set is the points on the boundary as well as on the interior of the set. Now, suppose let us take a point which is this point. So, suppose for some objective function, this point is our solution. Now, at this point only this constraint is active. So, the only constraint which is active at x star is this constraint. Now, other constraints are inactive. That means that the other constraints, this constraint, and this constraint, they follow hj x star less than 0, while this constraint follows hj x star equal to 0 or it is satisfied with equality. Now, suppose we perturb this constraint a bit. So, suppose we perturb this constraint to something like this, and we get a new solution, suppose which is somewhere, suppose this point is the new solution. Okay. Now, remember that at the new solution, the same constraint is active. This constraint which was here, it got perturbed to this constraint. So, let us assume that at the new solution, the same constraint is active. Okay. Or in other words, we perturb the constraint by a small amount, so that the set of active constraints do not change at this new point. So, suppose we perturb this constraint by some amount epsilon, then let us call this point as x star epsilon. And remember that the same constraint, so this was the active constraint at x star, and now this is the same constraint which is active at x star epsilon. Now, one crude way to check the change in the objective function is to resolve the problem, but without resolving the problem, can we find out or can we get a rough idea about how much will be the change in the objective function if we perturb this constraint by epsilon, and that is what we want to study. Okay. So, x star is a regular point and is a local minimum. So, the first order KKT conditions are satisfied, and in other words, gradient f x star plus sigma j belong to the active set, lambda j star gradient h j x star is 0, or in other words, x star lambda star is a KKT point. Now, suppose we perturb the constraint a bit, and we write a new constraint as hjx less than or equal to epsilon into norm of gradient hjx star. Now, this norm is taken just to get just to do the normalization. So, let us assume that epsilon is greater than 0. Now, how much effect such perturbation of the constraint will have? So, so here we have picked one constraint which is active. So, hj tilde is a constraint that is perturbed. So, this should be j tilde belong to Ax star, and this is going to be our new constraint. So, the problem that now we are looking at is to minimize fx subject to the same constraint as we had, except the constraint associated with j tilde. So, the same constraints hold for this, and for the j tilde constraint, hj tilde x is less than or equal to epsilon into norm of hj tilde x star. So, only one constraint got changed, and as we showed in the diagram that only one active constraint was perturbed. Now, how much will be the change in the objective function? That is what we want to see. So, let us assume that x star epsilon is a solution of the new problem, because the process one of the constraints, one of the active constraints got perturbed. So, suppose that new solution is x star epsilon. Now, one important assumption that we make is that the set of active constraints at x star and the set of active constraints at x star epsilon are the same. So, the perturbation is not large, but it is small enough so that the set of active constraints remains the same. Now, if we look at the constraint hj tilde x which is perturbed, we know that hj tilde x star was 0, because that was the active constraint, and xj tilde epsilon x star epsilon is nothing but epsilon norm of h z tilde x star. So, h z tilde x star epsilon minus h z tilde x star is a quantity by which the constraint got perturbed. Now, if we use the first order Taylor series approximation, then the quantity on the left side, in fact, if we write h z tilde x star epsilon as a affine approximation of h z tilde at x star. So, what we get is h z tilde x star epsilon is equal to h z tilde x star plus x star epsilon minus x star transpose gradient h z x star. So, this quantity on the left side is nothing but x star epsilon minus x star transpose gradient h z tilde x star, and that is approximately equal to the quantity on the right side. Note that we are talking about the first order approximation, that is why this approximation sign is there. Now, for the other constraints which were active at x star, they also were active at x star epsilon, because we changed only one constraint. So, for those constraints, this quantity is, the difference between these two is 0, or in other words, if we again do the first order Taylor series approximation, so this is approximately equal to 0. So, now let us look at the change in the objective function. So, we can write f of x star epsilon as a affine approximation around x star, and that will be f of x star plus x star epsilon minus x star transpose gradient f x star. Now, here we use the KKT condition. Now, we know that x star is a KKT, x star lambda star is a KKT point. So, gradient f x star can be written as negative of sigma gradient lambda j star gradient h j x star, where j varies over the set of active constraints. So, this quantity is written as this minus sigma j belong to x star minus x star epsilon minus x star transpose lambda j star gradient h j x star. And we have seen that except the j tilde constraint, this quantity x star epsilon minus x star transpose gradient h j x star is 0 except for the j tilde constraint, and for the j tilde constraint this will be lambda j star epsilon into gradient h z tilde x star. Now, epsilon is a small positive quantity. So, we can take epsilon on the left side and then take the limit as epsilon tends to 0, and therefore, so what we get is df by d epsilon at x equal to x star is proportional to negative of the Lagrange multiplier for z tilde constraint. So, what it means is that if we perturb one particular constraint, the change in by a small amount, the change in the objective function is proportional to the negative of the Lagrange multiplier of that constraint. So, this gives us some idea about how much will be the change in the objective function when a particular constraint is perturbed. But note that all this analysis was done based on the assumption that the active set remains the same at the new solution. If the active set changes, then this analysis does not hold. But the important point to note is that this Lagrange multiplier gives us some idea about the change in the objective function if a particular constraint is perturbed. So, if the Lagrange multiplier for a particular constraint is small, the change in the objective function could be small if that constraint is perturbed. This is also called economic interpretation of Lagrange multipliers or sensitivity analysis. Now, let us go back to the nonlinear programming problem that we considered, a general nonlinear programming problem where we minimize f(x) subject to the constraint h(x) less than or equal to 0 and ex equal to 0. And we saw the first order KKT conditions for this problem, and now we will see the second order conditions for this problem. These conditions we will see without giving any details of the proof. So, let us assume that f, h's and e's, they belong to the class of twice continuously differentiable functions, and let us denote the constraint set by symbol capital X, and let us take a point x star which is feasible. So, as we saw last time, the active set of x at x star is the set of all inequality constraints of the type Hj star equal to 0, and all the equality constraints, we have m equality constraints. So, all those constraints constitute the set of active equality constraints. So, this put together we get the active set at x star to be the union of the two sets I and E. So, we assume that x star is a regular point. So, that is the gradient Hj star j belongs to I and gradient Eix star I belongs to E is a set of linearly independent vectors. Now, we define the Lagrangian function as a function of x, lambda and mu, and the function is defined as the objective function plus linear combinations of the inequality constraints plus the linear combination of the equality constraints. Now, remember that whenever we define the Lagrangian function and the constraints are written in the form, the inequality constraints are written in the form Hj less than or equal to 0, then in this Lagrangian, these lambda j's, which are the Lagrangian multipliers corresponding to the inequality constraints, they are non-negative. So, under these function representations, and if you write the Lagrangian like this, these lambda j's are non-negative. And note also that there is no sign restriction on the mu's which are associated with the equality constraint. So, there are L inequality constraints. So, there are L lambdas which are non-negative, and there are M equality constraints. So, there are M mu's which are not restricted in sign. Now, let us look at the second order necessary conditions for this nonlinear programming problem. So, if x star is a feasible point, is a local minimum of this NLP and is also a regular point, then there exist unique vectors lambda star and mu star such that the gradient of the Lagrangian vanish with respect to x vanishes at x star, lambda star, mu star. And in addition to that, the complementary slackness conditions hold, that is lambda j star Hj star is 0 for all inequality constraints and lambda j stars are non-negative. So, I have already mentioned here, but that lambda star belongs to RL plus. So, what it means is that it belongs to the set of non-negative real numbers, but this condition is again explicitly stated here. Now, as I mentioned earlier, many times you will see that the feasibility conditions of x star are also written here, that Hj star less than or equal to 0 and Eix star equal to 0, but we have already assumed that x star belongs to x. So, that means that those conditions are always we are considering x star such that those conditions are satisfied. So, those conditions are not explicitly mentioned here. So, these were the part of the first order conditions. Now, if you recall, when we studied unconstrained optimization, the first order necessary condition was that if x star is a local minimum, then gradient f x star equal to 0. So, here instead of gradient f x star, we have gradient of L with respect to x evaluated at x star, lambda star, mu star is 0. So, this algebraic condition is easy to verify. Now, the second order conditions have some additional details, and those details are that if we consider the Hessian matrix of the Lagrangian evaluated at x star, lambda star, mu star, then that Hessian matrix is positive semi-definite along the directions D such that gradient Hj x star transpose D is less than or equal to 0, where J belongs to I, and gradient Ei x star transpose D is equal to 0 for I in the set of equality constraints. So, if we take the active inequality constraints, then for those constraints, if we write down the set of directions D such that gradient Hj x star transpose D less than or equal to 0, and for the all the active or for all the equality constraints, if we consider those D's which satisfy gradient Ei x star transpose D equal to 0. Now, this D put together form a set, and we choose any D from that set, and the Hessian of the Lagrangian should be positive semi-definite along any of those directions. So, these are called the second order KKT necessary conditions. Now, let us look at the second order sufficient conditions for the nonlinear program. Now, if there exists x star which is feasible, lambda star which is a vector of non-negative real numbers, and mu star in Rm, because there are m equality constraints. So, mu star in Rm such that these conditions hold. The gradient of the Lagrangian is 0, complementary slackness conditions hold, and all the lambda j stars are non-negative. Now, in addition to that, if we consider all non-zeros D's such that if we take the active inequality constraints which have positive Lagrangian multiplier, then for them gradient Hj x star transpose D should be 0. We take all the active inequality constraints for which the lambda j star is 0, for them gradient Hj x star transpose D should be less than or equal to 0, and if we take all the equality constraints, for them gradient Ei x star transpose D is equal to 0. Now, if we consider the set of D's which non-zero D's which satisfy this, and then take any D from that set, the Hessian of the Lagrangian should be positive definite along those directions. If that condition is satisfied, then we say that x star is a strict local minimum of NLP. So, let us again look at the unconstrained optimization problems, and we saw that D transpose for the unconstrained optimization problem, we saw that the Hessian matrix is positive definite. Now, since we are talking about unconstrained problem, there were no restrictions on D at that point. Now, we are talking about a constraint problem. So, D transpose the Hessian of the Lagrangian into D should be greater than 0, or in other words, the Hessian of the Lagrangian at x star, lambda star, mu star should be positive definite for all the directions D, which all the non-zero directions D which satisfy these conditions. Now, the proofs of these conditions, one can find them in standard reference books, but in today's class what we will do is that we will consider several examples and see how to make sure that the KKT conditions are used to solve or to get a solution of a nonlinear programming problem. So, the first example that we are going to look at talks about the existence and uniqueness of Lagrangian multipliers. Under what conditions do the Lagrangian multipliers exist, and under what conditions are they unique? So, let us consider a problem where we want to minimize minus x1 subject to x2 minus 1 minus x1 cube less than or equal to 0, x1 greater than or equal to 0 and x2 greater than or equal to 0. Now, we have already seen this problem, and we also saw that 1 0 is a strict local minimum of this problem. So, let us consider the problem. Minimize minus x1 subject to. So, let us write the problem in our required form, and that is 1 minus x1 cube less than or equal to 0. And then we have the constraint x1 greater than or equal to 0 and x2 greater than or equal to 0. So, we will write those constraints as minus x1 less than or equal to 0 and minus x2 less than or equal to 0. Now, let us look at the constraint set, and the constraint set is, so we have x1 and x2 as the two axes, and so this is the constraint x2 equal to 1 minus x1 cube, and we are talking about the points which are less than or equal to this. So, our constraint set is going to be the region shown here by shaded lines. Now let us look at the Lagrangian of this problem. So, the Lagrangian of this problem, remember that Lagrangian is a function of x as well as the lambdas and mu's, as is the case, but we will drop that representation for the time being. We will just mention L, we will assume that L is a function of x as well as lambda and mu. So, L is nothing but the objective function plus we have the first constraint, which is x2 minus 1 minus x1 cube, the second constraint, which is minus x1 less than or equal to 0. So, we have minus lambda 2 x1 minus lambda 3 x2. So, the gradient of the Lagrangian with respect to x, we will write it as minus 1 plus 3 lambda 1 minus x1 square minus lambda 2, and with respect to x2, it is lambda 1 minus lambda 3. This is the gradient of the Lagrangian. Okay. So, if you recall that we had seen earlier that this point is x star, which is 1 0, that is a local minimum of this problem. We want to minimize minus x1 means maximize x1, and that with respect to this feasible region, it the minimum occurs at this point, or the maximum x1 occurs at this point. Minimum of minus x1 occurs at this point, or maximum of x1 occurs at this point. So, let us see what happens to the KKT conditions at this point. So, let us consider the case where we have x star to be 1 0. Now, at this point the constraint x1 greater than or equal to 0 is inactive. Only two constraints are active, the first constraint and the third constraint. So, the second constraint is inactive. So, x1 star equal to 1, which is greater than 0, and therefore, the second constraint x1 star greater than or equal to 0 is inactive. Therefore, the second constraint is inactive. And therefore, what we have is lambda 2 star will be equal to 0, because second constraint is inactive, and we saw earlier that for the inactive constraints the corresponding Lagrange multipliers are 0. So, now let us look at this equation. So, the KKT conditions, what they say is that the gradient of the Lagrangian should vanish at a KKT point. Okay. So, what we have is gradient of L with respect to x should be 0, and then lambda star transpose x star should be 0 and lambda star greater than or equal to 0. So, let us use these KKT conditions at this point and see what happens to the Lagrange multipliers. So, the gradient of L with respect to x at x star lambda star, so is nothing but, so let us put these values of x star in the gradient of the Lagrangian. So, the gradient of the Lagrangian, we put x star, x1 star to be 1 and x2 star to be 0, and then equate that to 0. So, what we get is minus 1, because x1 is 1. So, this quantity vanishes, and what we get is minus 1 plus minus lambda 2, and since the second constraint is inactive, lambda 2 star is 0. So, what we get is minus 1 and lambda 1 star. So, the second constraint lambda 1 minus lambda 3 should be 0, or in other words lambda 1 star minus lambda 3 star should be equal to 0. Now, if you look at this, we have minus 1 equal to 0. So, that means that so this is not possible. And the reason why we came up with this condition is that the point is the point x star is not a regular point. So, if we consider the gradient of f x star, so the gradient of f of x star will be in this direction. Then the second constraint is inactive. The third constraint, its gradient is 0 minus 1. So, gradient h3 x star is along this direction, and the gradient of the first constraint will be along the direction 0 1. So, this will be the gradient h1 x star. So, you will see that the gradient h1 x star and gradient h3 x star, which are the gradients of the active constraints at this point, they are not linearly independent, and therefore, x star is not a regular point. and therefore, we are not able to find a KKT point, although this point is a local minimum, strict local minimum of the problem, we are not able to get the KKT point. So, 1 0 is a strict local minimum, but we cannot find a KKT point, and the problem is that the linear independence constraint qualification does not hold at 1 0. The gradients of the two constraints which are active, the first and the third constraints, they are not linearly independent at this point, and therefore, the linear independence constraint qualification does not hold, and therefore, we cannot find the KKT point involving this local minimum. Now, let us add an extra constraint to this problem. So, the extra constraint that we are going to add is 2x1 plus this should be x2, 2x1 plus x2 plus is less than or equal to 2. So, that is so this constraint is 2x1 plus x2 less than or equal to 2. So, let us see what happens when we add that extra constraint. So, we have the same problem. And then we have the constraint. So, this was our earlier problem, that x1 greater than or equal to 0, x2 greater than or equal to 0, and x2 less than or equal to 1 minus x1 cube. And to that we add a constraint. So, let us write down the constraints: minimize minus x1 subject to x2 minus 1 minus x1 cube less than or equal to 0, minus x1 less than or equal to 0, minus x2 less than or equal to 0, and we have added one constraint which is 2x1 plus x2 less than or equal to 2. So, this is the extra constraint that we have added. Now, let us see how this constraint looks like. So, it passes through this point on the x axis. So, and then on the x1 axis and the x2 axis. So, it cuts the x2 axis somewhere at this point. So, we can write we can draw that constraint to be a line passing through 0 2 and 1 0. Now, if we look at the constraint, so what we want is that x1 x2 should satisfy 2x1 plus x2 less than or equal to 2, or in other words the points below this line. So, this is the line 2x1 plus x2 equal to 2, and we are interested in the region which is on this side of the line, and that intersection of that region with our earlier constraints. So, you will see that our earlier constraint, which was this region, shaded region here, that remains the same, that has not changed. So, in other words, this point x star, which was 1 0, is still our local minimum, because the constraint set is not changed. Now, let us look at the Lagrangian. So, let us write the Lagrangian again the same way as we wrote last time, plus lambda 1 into x2 minus 1 minus x1 cube minus lambda 2 x1 minus lambda 3 x2, and now we have another constraint. So, we have lambda 4 into 2 x1 plus x2 minus 2. Now, if you look at this point again, so again at x star to be 1 0, we have lambda 2 star 0 because this constraint is inactive. The other three constraints x2 equal to 0 and then x2 equal to 1 minus x1 cube and 2x1 plus x2 equal to 2. So, all the remaining three inequality constraints are active, and therefore, if you write down the KKT conditions, so gradient of L with respect to x equal to 0, this implies what we get is minus 1 plus. So, let us substitute at this, let us find the Lagrangian at this point x star, and we want to find out the corresponding lambdas. So, minus 1 plus, so this quantity vanishes, lambda 2 is 0. So, we have the gradient with respect to x 1. So, we have 2 lambda 4 and the gradient with respect to x 2. So, that means we have lambda 1 plus lambda 4 minus lambda 3 plus lambda 4. Is equal to 0, and this means, and therefore, lambda 4 is equal to half, lambda 4 star is equal to half, and lambda 4 star is equal to half, and that means that therefore, lambda 1 star minus lambda 3 star is equal to minus half. So, what does this mean is that, so this means that we can choose lambda 1 star and lambda 3 star to be greater than or equal to 0, such that their difference is the difference between lambda 1 star and lambda 3 star is minus half. So, lambda 2 star is 0, lambda 4 star is half, and lambda 1 star and lambda 3 star can be chosen such that they are non-negative and their difference is minus half. So, that means that the number of Lagrange multipliers is not unique in this case. Now, if you look at the first order KKT necessary conditions, we made a statement that if x star is a regular point, then the Lagrange multipliers are unique. So, in this case, since x star was not a regular point, here is a situation where we do not get unique Lagrange multipliers. Now, let us look at other example. So, this example is about the representation of the constraint set. So, the way we represent the constraint set is more important rather than the constraint set itself. Constraint set anyway is important, but the way we represent it can decide whether a particular point is a KKT point or not. So, let us take an example where we want to minimize this quantity x1 minus 9 by 4 square plus x2 minus 2 square. Now, subject to the constraint that x square minus x2 is less than or equal to 0, x1 plus x2 less than or equal to 6, and x1 and x2 are non-negative quantities. Now, this is a convex programming problem because all these functions, the function f and hz all are convex functions. There are no equality constraints. So, this becomes a convex programming problem. So, for a convex programming problem, we have to look for the Slater's constraint qualification, which mean that there should at least exist one point which is in the interior of the set. So, let us look at this problem. So, the problem that we are looking at is minimize x1 minus 9 by 4 square plus x2 minus 2 square subject to the constraint x1 square minus x2 less than or equal to 0, x1 plus x2 less than or equal to 6, and x1 greater than or equal to 0. So, minus x1 less than or equal to 0 and minus x2 less than or equal to 0. So, if we draw the feasible region, so we have x1 and x2 as the two axes. Now, x1 square equal to x2 is a parabola. So, is a parabola. So, we are interested in the points above this parabola because x1 square should be less than or equal to x2. So, the points above the parabola, then x1 plus x2 equal to 6. So, that line suppose like this. So, this is the line x1 plus x2 equal to 6. So, the point of intersection of these two curves is 2, 4. And so, we are interested in the points above the parabola, below this line, and in the points which are in the first quadrant. So, if we look at the feasible set, the feasible set is shown here. Now, we want to find out the point on this feasible set which is closest to 9 by 4 comma 2. So, the point 9 by 4 comma 2 will be somewhere here. So, this point is 9 by 4 and 2. So, we want to find the point in this feasible region which is closest to the point 9 by 4 comma 2. Okay. So, so there are different possibilities. One possibility is that the point 2, 4 itself is a minimum point, or the minimum point lies on this curve. So, this curve is nothing but x1 square is equal to x2. So, either the minimum lies on this curve or the minimum is here. Obviously, this point cannot be a minimum point, or you cannot get a minimum either on this line segment or this line segment. So, let us look at these possibilities. Now, for that purpose, let us write down the Lagrangian. So, the Lagrangian is the objective function. So, x1 minus 9 by 4 square plus x2 minus 2 square plus lambda 1 x1 square minus x2 plus lambda 2 to x1 plus x2 minus 6. Now, we still have two constraints. So, minus lambda 3 x1 minus lambda 4 x2. So, these are the 4 constraints, and then the correspondingly the Lagrangian will look something like this. Now let us see what happens at 2, 4. So, let us consider the case that at x star equal to 2, 4. So, what we have to do is that let us write the Lagrangian, and that Lagrange let us write the gradient of the Lagrangian, and that should vanish. So, if we calculate the Lagrangian, the gradient of the Lagrangian, and then calculate it at this point, so what we get is so the derivative of this term with respect to x1 is 2 into x1 minus 9 by 4, and if we substitute x1 star to be 2, so what we get is minus half. And then the next thing that we get is 2 lambda 1 x1, and 2 lambda 1 x1 at x1 is equal to 2 is 4 lambda 1. So, 4 lambda 1 and plus lambda 2 and since x1 is greater than 0 and x2 is greater than 0, the lambda 2 star and lambda 3 star and lambda 4 star are zeros. Now, the derivative with respect to x2. So, 2 into x2 minus 2. So, x2 star is 4, 4 minus 2 is 2, 2 into 2 is 4 minus lambda 1 plus lambda 2, and that is equal to 0. Now, if we solve this, so if we subtract the second equation from the first equation, so what we get is, so therefore, what we get is 5 lambda 1, the lambda 2 will get cancelled and that will be equal to 4 plus half. So, 4 plus half is 9 by 2, or lambda 1 star is equal to 9 by 10. Now, if we plug in this value of lambda 1 star here, so what we get is lambda 2 star is equal to 9 by 10 minus 4, and this quantity is, so this quantity is less than 0. So, therefore, lambda 2 star is less than 0, and therefore, x star equal to 2 4 cannot be a KKT point. And the reason is that at x star we got the value of lambda 2 star to be less than 0. So, this quantity which was less than 0, and if you recall our KKT conditions, we wanted the Lagrange multipliers to be non-negative, and certainly we are not able to get non-negative Lagrange multipliers for this x star. So, this 0.24 is not a KKT point. Now, the case that needs to be checked is whether the solution lies on this curve. So, if the solution has to lie on this curve, so only the first constraint will be active, the rest of the constraints will be inactive, and therefore, the lambda 2 star, lambda 3 star and lambda 4 star will be 0. Let us assume that the solution does not lie here, but it lies in the on this curved line from this to this, and 2 4 is not a solution, is not a KKT point. 0 0, let us assume that is also not a solution. So, the idea is to get a point on this curve which could be closest to 9 by 4 and 2. So, once we assume that the 3 Lagrange multipliers are 0, then it is easy to write the Lagrangian and take its gradient at a point, at a suitable point on this, and we will see that in the next class. Thank you.